Hi students, and today in this class I'm going to teach you about the wavelength selectors, which is one of the most important component of spectrophotometer. By using this component we can get the exact wavelength to analysis, and this is the place where I am sitting. Just you can see that this is the nature of a village, right? And this is a small canal which is used to irrigate these fields. Oh, and sure, each and every spectrophotometric analysis requires the radiation, right? And any form. If we are using UV spectrophotometer, we need UV visible, or if we are using IR, we need a IR radiation, right? Those radiation should be in exact bandwidth, right? So the limited, narrow, continuous group of wavelengths are called as bands, which is we needed actually. Narrow bandwidth enhances the sensitivity. So it means how can we find that the bandwidth is narrow? So it means you should measure the transmittance, right? You see here in the picture, percent transmittance with wavelengths, right? Percent transmittance versus wavelength. In this curve, which is denoted in the blue color line, the half of the height is called as the bandwidth, a effective bandwidth, right? Okay, effective bandwidth. Nice. Strictly speaking, there is no wavelength selector till now it is identified to give exact wavelength. Suppose if I want 200.8 lambda, which means nanometer, means there is no wavelength selector to give the exactly 200.8, but it can produce some narrow bands. From that we can select. Okay, so effective bandwidth means a full width at half peak height, which determine the quality of our analysis. Okay, then how can we classify the wavelength selectors? Wavelength selectors broadly classified into filters, monochromators, and others, which means the advanced wavelength selectors. Otherwise you can say this is newer wavelength selectors. Okay, the filters again we can classify it into interference filters and absorbance filters. The name itself says it is interference, which means the incoming radio waves or incoming EMR get interfere with each other and produce the wavelength in, right? That is called as interference wavelength. For example, Fabry Perot et al. Is nothing but the sandwich model. I will show you in the next slide. And the wedge shaped interference, right? Wedge, that is a shape like triangular shape, that is a wedge shaped interference. And the third one is holographic interference, the very most and advanced, and it also getting advanced day by day, or by each and every advancement is holograph makes a new things, right? Okay, which is furtherly we can divide it into surface hologram and volumetric holograms. When come to the absorbance filter, those are very simple and classical, which is made by glass or any transparent material. Mostly those are colored materials, which is going to be absorb the bandwidth, or going to be absorb the spectrum of the light, and it can transmit the any one type of wavelength through this material. So that's why it is called as absorbance wavelength. And here monochromators, so we can clearly define that monochromators means it can, mono means single, chromatar means colors, a single color it can transmit or it can produce single wavelength. It can divide it into prism monochromator and grating monochromators. Prism we already knew, that is a crystal, right? Triangular crystal. We can make it to use for refraction or reflection of the light waves, right? We can get it VIBGR by using prism. So for example, Carnot prism and litho prism. These are two different prisms we are using for as a monochromator. And grating, that is most important, and it is called as sometimes master grating, right? It can produce the exact wavelength, most accurate one, nearly 99.8 or 99.5 to 9.8. It can produce the exact wavelength by the grooves, right? Actually it has gratings are nothing but the lines which is produced in the glass plates or any transparent materials. In the line, the light waves get reflected or transmitted and gives the wavelength, exact wavelength. Okay, and the most important thing is those lines are produced by or drawn by using a diamond tool, right? So we can give nearly 1000 to 3000 lines in okay, so which are done by automatic machines. Other wavelength selectors, you can see polychromators. It can produce wide range of spectrum. From this we can select any whatever we want, any one of the nanometers. Okay, spectrographs and acoustic optic tunable filters. Okay, these are the new year's one. Interference filter, the first filter is very simple, and first filter is interference filters. You can use this as an example to write in your examinations. So it provides narrow bands of radiation through optical interference, right? Because interference filter, obviously it should produce interference. So an interference filter consists of, you can see that in picture. Okay, why it is not coming? See in the picture, this is the interference filter. White radiation is impinged on the surface of the array. That in the core, in a central part, you can see that is white in color, that is dielectric layer, which is filled with dielectric components, mostly metal halides, calcium fluoride, magnesium fluoride. Those are the dielectric components used here. And this thickness of the dielectric layer is mainly used to get the exact wavelength, or depends upon the thickness the wavelength it is produced by this interference filter. Okay, the dielectric layer is sandwiched by using metal films, right? So semi transparent or transparent are used. Apart from this, you can find the whole protection by using fully transparent glass plates, right, which is in blue in color. Okay, so now you can explain that this figure, the core is dielectric layer which is white in color, the distance is most important, and the next is block in color which is metal film, and the blue, again blue in color, is glass plates which is covered entire thing. Okay, now we can see that how it is works. Okay, see, transparent dielectric, example calcium fluoride or magnesium fluoride layer, two semi transparent metallic films, and the next one is this total thing is covered with transparent materials such as glasses, right? The thickness of the dielectric layer determines the waves of the transmitted radiation. That is what we have to check, and we have to make according to our wavelength needs. Now how it works: when the perpendicular beam of parallel radiation strike the array, which means the surface, array means the whole setup is called as arrays. When it strikes on the surface, a fraction passes through the first metallic layer and the remainder is reflected, right? Actually 50% of the light rays is get reflected and 50% gets transmitted. That's depend upon the dielectric elements we are using. Okay, understood that the first metallic layer gets reflection and transmission, and the portion is passed and undergoes a similar partition when it strikes the second metallic film, right? First of all, the first metallic film, where the light rays gets transmitted and reflected, and the same thing is happened in the second metallic layer. So if the reflected portion from the second integration is of the proper wavelength, means it is partially reflected from the inner side of the first layer in phase with incoming light of the same wavelength. That is the main thing. The reflected wavelength which is reflected from the second layer is again struck by the incoming wavelength which has the same wavelength, incoming light which has the same wavelength. So the particular wavelength is reinforced, most other wavelengths being out of phase, and this is what happened in laser also, laser production, right? So the same wavelength get constructive and became reinforced, others are out of plane, so those are destructive wavelengths, so it get destruction. Okay, because interference filters separate light into transmitted and reflected beams, they are sometimes referred as dichroic filters. Okay, so these interference filters are transmitted and reflected films. So two types of oxys happening here, which means transparent and transmittance transmittance and reflectance. So that is called as dichroic filters. Then you can see this. This is the example of the two layer, right? Two arrays of the two layer. For example, in this picture, the number 1, in the light waves get impinged on the surface of the layer 1, and the 50% is reflected, that is denoted as 1, right? And the 50% is transmitted to the next layer, right? From there, in the next layer, it gets again transmitted and reflected. Okay, that reflection is 1 dash as per the picture. That 1 dash is again hit to the previous layer by reflection, that also interfere by the incoming new radiation which has the same wavelength, or after the interference it produces the same wavelength, so it get reinforced. Hope you are all understood. Okay, Fabry, Perrot, Etalon. Etalon is nothing but the sandwich model, same like the interference filter. This is the example for that actually. It consists of a plate made up of transparent material coated with non-absorbing. So it is going to be a reflection or transmittance, right? Transmitting the waves. So it is not going to be absorb any wavelength. Okay. A spacer of the chosen thickness made by invar. Invar is nothing but a metal alloy made up of nickel, I think. I don't have remember that. So if you want, you can check it in internet. That I know that surely it is a metal alloy. Okay, or quartz. Quartz is a glass, one type of glass, right? With highly parallel faces of sandwiched between two mirrors to form the etalon, right? There are two highly reflective mirrors make the etalon. I will show in the picture. Bandwidth is determined by the reflective of the coatings of mirrors. The separation of the transmitted band is dictated by the distance between the mirrors. The same thing we see in the previous slide, right? So I forgot to show you in the previous slide, and see that the D, see, D is the distance between, or the distance covered by dielectric layer. Okay, so that is most important. You can see that you can derive that lambda equal to 2dn by n, and here lambda equal to required wavelength, and 2d is the reflection path ways, right? It gets two times, right? It gets 2 times reflected. any light rays which can produce the wavelength, that means a reinforced wavelength. Okay, that's why we put 2D, and n is the number, again the number of reflection. Okay, and come to the next slide. You can see that the talent may be tilted, means we can tilt that same position of the wavelength selector, which means Fabry-Perot talent, to get the different wavelengths from smaller to the lengthier one. Okay, separation can be adjusted mechanically. The device is called Fabry-Perot interferometer. This interferometer is one of the most important setup which is used in infrared FTIR. We will see that setup during FTIR instrumentation. So now you can just understand that interferometer is a setup with mirrors to produce different wavelengths because of adjusting the mirrors, two mirrors, right? Okay. Which is used in laser experiments, spectroscopy, and in fiber optic communications. Isolating very narrow bandwidth of radiations. These are the application of Fabry-Perot talent, and this is the block diagram of that talent. See that blue color vertical bars are mirror 1 and mirror 2. What happens, it is transparent or semi-transparent, right? What is that? That input light, which is incident light, which is a green in color, arrowhead, which goes and transmitted through the first mirror and hit the second mirror. From the second mirror, 50% of the light is get transmitted and 50% is again get reflected. That reflection goes and hit the again M1, that means mirror 1, right? So by this way the light waves get hitted, reflected, transmitted, right? So we can get the exact wavelength from this when we adjust the focal plane. Okay, this is the exact mechanism of Fabry-Perot talent. So number of wavelengths produced equal to 2D mu cos theta, that is the angle of the light impinges, right? This is called as cos theta. Okay, interference wedges. I told you wedges means the shape, triangular shape. Here you can see that this is the wedge shape, that blue color bars. You maybe remember that wedge shaped organ in our body is liver, right? So in Tamil we can say it apu. That wedge is called as triangular shapes, right? In simply you can say the heels, right, and the chapels, right? That heels is a wedge shaped one, so don't forget that. That wedge shaped means due to the distance between two mirrors, because of that wedge shape, mirror distance is gradually increasing or gradually decreasing. By increasing or decreasing these dielectric constant layers, we can get the different wavelengths. That is the principle here working. Okay, it can be used in the place of prisms or gratings in spectrophotometers. Consist of pair of mirrored, same thing what we are seen in previous wavelength selectors, and partially transmitted plates separated by a wedge shaped layer of a dielectric material. So dielectric material we already knew, the metal halides or the calcium fluoride or magnesium fluorides are used. Okay, inorganic. The length of the plane ranges from about 50 to 200 millimeter. From that we can get each and every distance, we can get the different wavelengths. Okay, radiation transmitted varies in the wavelengths when the thickness of the wedges is varies. So mechanically we can move the layers, the entire setup. These filters can pass long wavelengths, right, and short wavelengths. So you can see this. This is the setup of how it is working. And air wedge is formed by two plates of glazes separated at one end. Actually we are not going to use any air in that instead of VR we are using dielectric components to fill that. Okay, and here this is the setup of plates actually with the gratings lines. You can see that black and green lines which is produced by arrays. Okay, interference edges are available for visible region and also IR regions, right? For visible region you can get for entire 200 to 800, that is actually visible UV and visible. So UV started at 200 nanometer, but it is minimum is 300, so we can effectively use in visible. Then IR regions, that is in nanometers, wavelength is in nanometer. Kindly note the point, we are using wavelength in nanometer in UV and visible, right? And here it's going towards the lengthier one, so it will be in micrometers actually. And see, it's 2.5 to 14.5 micrometers. If you want to convert, we can convert into micrometers, nanometers also, right? Actually we are saying in micrometers for IR radiations, otherwise we can get the number of frequencies. Okay, the most important are, you can use this holographic filters to explain your big questions, right? Holographic filters, so laser beam, it gets splitted by the beam splitter. So two type of waves it gets splitted, and one is going to hit the another mirror, and here it is going to the one more mirror, right, in the downside, and the straight one. So both are get heated, and again those light waves or any waves EMR are rejoined at the plates which has the photo emission or that photoelectric or emulsion containing plates like negatives. Okay, so it has the two types, we already knew that, surface and volume one. In the picture actually shown is surface one, so I have to show you, right? And this is this pink color arrowhead shows surface one with a substrate, and the another pink color, the shorter one, is called as the volumetric one, right? It has the image, you can find the image in the depth of our 3D hologram in the setup, not in the surface. How it works: the coherent radiation of laser beam impinges on the beam splitter. We have seen that in the previous slide. So redirection to the recombined at the surface of the thin photosensitive film, right? Actually they are using emulsion in that. Okay, that mutual coherent beams have a fixed phase and intensity relationship. They produce an extremely uniform interference pattern. Light and dark bars are fringes is nothing but lines all the surface of the film. Okay, the fringes sensitize the film which has photographic emulsion or photoresistive polymer layer. Sensitized areas are developed or dissolved away, leaving a grooved structure on the surface on the substrate. Okay, now we are using 3D hologram, virtual 3D hologram. We can set it anywhere, right? And this is the basic mechanism for that. The structure is then coated with aluminum or other reflective material to produce a holographic reflection grating. Okay, so it's better. Okay, these are the example of holograms. So you can see that the coherent light beam hit the beam splitter. From the beam splitter it splits into two waves, and one is illumination beam and another one is the it is going to just hit the mirror 1 and mirror 2. What happens, instead of mirror 2 we have an object, right? See this, we have any object, that object produce the waves in the different direction, which means and depend upon the shape what we have placed, right? So it again hit the first mirror produce the reference beam, and the second mirror there is no mirror, the object produce the object fringes. So both are hit at the photographic plate. From the photographic plate, reference layer is destroyed, or reference layer is not taken in account, right, to produce. So the rays from the objects get read and produce the hologram. Okay. Volume transmission hologram means the thick layer, nearly 100 micrometer, of photosensitive material sandwiched between the transparent layer, placed at the plane of intersection of two laser beams. The two laser beams is one is from the object and one more from the reference mirror, right? Okay. Interference fringes are formed through the volume of the film layer rather than just at its surface. There are two types. You can produce the hologram in the surface, and you can produce the 3D hologram in the inner part also by using the transparent box, right? When the two beams intersect at equal angles to the surface normal of the film, what happens? A wave modulator fringes pattern is formed, and the entire volume of the film get sensitized, and the pattern is read. Okay, these devices are also used as gratings and as a filters for removing undesirable radiation such as plasma lines and sinusoidal from laser radiations. Absorption filters. So I already told you it is going to absorb the light, a particular light, and it transmit any particular wavelength. Okay, absorb selection portions of spectrum. Selected portion of spectrum get absorbed. Okay, consist of colored glass, that is the classical one. So colored glass are dye suspended in gelatin. So gelatin also a transparent one, we mostly used for plates, right? Gelatinous plates we are using, which is the transparent one. So you can use gelatin with any dye to produce an absorption filters, and sandwiched between glass plates. Then colored glass filters have the advantage of high thermal stability when compared to that normal one. Okay, less expensive. I told you this is classical. And then interference filters used for band selection in the visible region. Kindly remember this. Mostly absorption filters are used for visible regions, right? Between up to the effective bandwidth in 230 to 250 nanometers. Absorb a significant fraction of the desired radiation and may have the transmittance of 10% or less than at their peaks bands. Okay, that's the disadvantage. So we can use cutoff filters which have the nearly 100% transmittance. So it transmittance more, so we can get the more bandwidth. The narrow spectral band can be isolated by coupling the cutoff filters with a second filters. Actually we can use, this is very simple and cost effective wavelength selectors, but it can produce only the range